motor controllers coming through, the power, and the power going to the motors, all routed internally. Our motor controllers here, we stripped the stock heat sinks off and heat sinked that to the chassis. It saved weight and also embedded them nicely inside. Here's our removable electronics bay. You can see here is our onboard computer. It's actually developed at Oregon State by undergraduate students, and it runs on Linux. And it goes to the USB hub, which then interfaces to each of these removable control cards. And these are all installed on a backplane, which allows us to just plug in the card and just use each system separately. So one of these cards has all our motor control functions, another one has the video functions, another one has GPS, another one has the pan tilt controls and the arm controls. And being able to just pull a board out like that and fix it or swap it out with one that does work was very, very useful. And it also looked really cool. And like in a computer, it's called an ISA bus or ISA protocol. We called this Rover bus because we customized it. So here's some of the testing. This is a picture of in our lab. This is the day before our first wireless test. It was probably somewhere around 4 or 5 a.m., something like that. We didn't get any sleep that night. Keep in mind this is spring break, so we're scrambling as if it's the weekend before Utah. You can see here is a piece of wood with a circuit board zip tied to the outside. It was very improvised. These sort of solutions we called Utah solutions because that's what we were used to the previous year. But we made sure that all that sort of thing was gone. So our first test was in Eastern Oregon. It snowed on us when we got there, spring break, and but it really gave rise to how well we designed our rover because it functioned just fine in the snow and it could handle precipitation and these sort of things. Performed very well. Here's us in the back of the van. This was our first shot at setting up a control station. Our laptop has all the navigational software on it and the user interface. This little screen right here, that is our monitor. We later upgraded to full size, but this is all we had at the time. The joystick here is what we use to control the rover. And this little PlayStation controller, that's what we use to control the arm. So we have two operators when we use an arm. Here's the environment where we tested out in Eastern Oregon. The terrain is very similar to Utah as well as the consistency of the ground is very sandy, so we chose this area. But as you can see, there's snow around, so that's about 80 degrees colder than Utah. But here's us, shot climbing up the hill. You can see some of these boards packaged in bubble wrap to keep them from the elements. That was all fixed as well. They were later installed inside. Then we decided our rover was a little too heavy, and in order to make the cut, we did some extra machining. You can see there's some. This is a little bit narrowed. We did a lot of this stuff, but it allowed us to sort of take all our parts, put them on a table, shine them up nice. So I can show you all that. Here you can see our motor controllers embedded in the bogies. These are arms that the actuator is attached to turn the wheels. These are pieces of the hubs. They interface the motors with the wheels. We had about 6 of these, 5 components each. These are the main bogie hinges. That's what holds the whole chassis together. And here's an overview of all the parts. So with the exception of this piece of aluminum here to electrical housing, it was our design, but we had it sent out for manufacture because we don't have the abilities to manufacture any sheet metal at our university. All the aluminum parts you see here were designed and machined by us at our university. We have a very great machine shop and a lot of good resources. The only thing we outsourced here was the welding job on this frame and on these bogies. But we made our own welding fixtures, had all that sent out for welding, then we did all the post-machining. It was very, very difficult. We have a stack of drawings about this thick that goes with this rover. So here's the fully assembled rover the night before we take it to Utah. All ready to go. You can see a very reflective surface on the top. That is because we discovered that in the sun, although aluminum is very shiny, it absorbs infrared very well. So we had a reflective mylar installed to reflect the infrared energy, and that kept our electronics much cooler. So in Utah, our task is to set up the command station. We had this nice trailer, which was a godsend, by the way. It allows us to set up a command module inside of there. We had about 16 people with us. Everyone had a task. We had checklists for everything. We had procedures outlined for everything so that we wouldn't make mistakes. Took 9 people alone to set up the antenna, which was a 25-foot tall mast. Here's us doing the pre-flight for the mechanical stuff. We had pre-flight for electrical as well. Here we're setting up the antenna mast, the 100-foot coax cable to go with that. There's the erected antenna mast, about 25 feet tall. And here's our command station inside of the U-Haul trailer. So we had 3 monitors. One is on the laptop here. That's all the navigation stuff. It shows us where we are on the map. We have a driver's monitor. That's what I was using. And we had a monitor for video capture. And thanks to that, you'll be able to see all our video. So here's a demonstration of how our chassis conforms to terrain very well. You'll see it flexes to it very well, but yet the main structure of the rover remains very stable. And this is something we were very impressed by ourselves. Throughout the design, we sort of discovered that this thing was going to be able to do some amazing things, and we built it, and it sure did. So here's some overnight work the day before the competition. Since we had such a reliable rover, we were able to be pretty greedy, so we added an audio system to it so we could get audio feedback as well. So unfortunately, it only picked up higher frequency stuff, so it sounded more like we're driving around a Sherman tank than a very silent electrical rover. It was pretty fun. And a lot of fun. We got enough sleep. So you can see some of the lights on at night. These blue lights are our motor controllers. Some of the green lights here are DC-DC converters and status lights on our fabricated circuit boards that we had designed and sent out for fabrication. And that's our computer. So here's us at the equipment servicing task. You can see our shiny reflective surface reflecting all the sun's infrared energy there. Here we're flipping the first switch. And you can see this is our Cartesian coordinate arm, very much like York's, independently designed. We didn't know what they were working on until we had already designed ours. And grabbing the first plug, lifting it up, rotating it around. We had a sort of a wrist control on the end of our Cartesian arm, which allowed us to orient it correctly, and then with the Cartesian coordinates, we would move it into the correct position. And the plug's in. Here's the second task of that day. It's sample return. We had a scoop installed for this one, but on the same arm. Here we're investigating the first site. You'll see video of all this as well. This site here we didn't elect to actually take a sample from. It was frustrating for me as a driver and engineer. I just wanted to drive and dig, and our biologist kept looking around saying, no, how about we drive over here and look at there? And I was like, well, can't we just dig up a sample? Like, no, we got to move this way. It's important, we got to get the right sample. So it was a very realistic scenario, and I kind of understand where the engineering frustration now comes from when working with scientists, but it's very appreciated, and we did a good job. So here's the site where we decided to take a sample. We had a rock that looked of interest to our biologist, and we picked it up along with some of the soil surrounding it. So we had a little baggie attached that we could flip the scoop back, and all the soil would fall into it, and we could keep digging, so we could grab samples in stages. We didn't have to go for one big scoop at once. And you can see our camera's positioned far off to the side there. It allows us to get a good overview of what we're working on. So here's our sample. It's about 160 grams total, so we fit well within the limits. After day one, we retired our railgun. No longer needed because all of the tasks requiring the arm were complete. So there it is, one final go at it. Here's us driving up to the first supposedly unreachable marker. Was no problem for our chassis though, which saved us time in triangulation. There's another one we could drive up to. Here is the astronaut task. This is the one we were most afraid of. We had the most trouble with this last year. It's where our rover broke its chains, and we never even saw the astronaut that year. So this year, we were most prepared, I think, for this one, and also most afraid. But the astronaut was told by our judges to be headed in this general direction when last seen. So we figured we would go through between those two hills and start looking. We also had the help of a last known GPS location, which also was somewhere in that area. So that confirmed that. So we headed over there, climbed up this hill, which wasn't much of a hill. I was hoping to be able to drive over all these hills and stuff because I really wanted to just drive over hills. But it ended up being much easier than that because there it was right on the other side. It only took us 3.5 minutes to find it. So that was by far a record for the event. So we got there, we're like, oh, now what, is that an astronaut? The guy, our judge asked, and we said, well, it looks like a spacesuit with a big red number on it. He's like, well, are you calling that the astronaut? I'm like, it looks like one, I don't know, did you guys put another one out? I don't know. So we confirmed that, and we celebrated.